Can you please confirm if I'm audible? Uh, can you confirm? Yeah, thanks. So yeah, I think we are on time now. So let's start for the live session for week 8 for the course Semiconductor Device Modeling and Simulation, which is taught by Professor Vivek Dixit from IIT Kharagpur. I'm Anant Singhal, a PhD student from IIT Jodhpur, and today I'll be assisting you in solving some of the similar assignment problems that have been given to you in your week 8 assignments. So yeah, before we move forward, we let's see the course outline, and we have reached the modeling part of this course because in the last week also we did discuss some of the functions or some of the equations that we have in the modeling aspect, such as the distribution function. We discussed about the Fermi Dirac distribution function. Then we also discussed very briefly about the Boltzmann transport equation. RTA is very straightforward, so there's a derivation that is present in the theoretical lectures. If you want to have an in-depth analysis, you can check that. But it is very straightforward, so I did not cover it. And at last, we covered some of the scattering and mobility problems and some of the concepts of scattering and mobility and how does it happen in the actual semiconductor device. So now, I mean, the initial weeks involved complete analysis of the devices that are there, and the later part of the course involves the models. So the mathematics around these devices and the and the physics that is present is what we call as models that I already explained in the first lecture of this course. So as you can see in this particular course, we'll be discussing more about the drift diffusion models, which is the topic for both week 8 as well as week 9, in which we'll be discussing some of the drift diffusion models that we have in our syllabus. So we have some topics such as drift diffusion model derivation. So I'll try to have a very brief explanation of the derivation of the drift diffusion model that we have. Then we use Taylor series expansion and FDM, that is a finite difference method, to have some approximations in the derivation. Then Poisson equation we have kind of already covered, and there is some more linearization or some approximation of that we may cover. And in the next week also there are this generation and recombination models. So I'd say this is the important topic because most of the models or the tools that you are using are using is the generation and recombination models. So we'll be discussing some of the generation recombination models such as SRH model. Then there is auger recombination model, etc. So yeah, in the subsequent 2 weeks, today and the next week, we'll be covering more or less the drift diffusion part, and then we'll move to the later part of the modeling that is mentioned in the subsequent course. So let's start. As we said, that the main topic for this week and the next week is the drift diffusion model. And if I say in details, we have already covered the kind of the drift part because when we were studying about the kind of diffusion or sorry kind of conduction that we have in a MOSFET, that was due to the drift, and we there calculated about the drift velocity that was around, if you remember, it was VD, that is equals to mu e. So the drift component was due to the electric field application. So once we apply the electric field, there is the drift component, and there we discussed that diffusion component comes from the change in concentration, right? So where we did not discuss about the derivation of the change in concentration or the diffusion model aspect. So we will be covering this diffusion model derivation in this particular lecture. So if you remember, the total current density components that we were discussing was different for different type of material. So let's say for N type, if I try to write the drift component, the complete drift component was for N type and it was for P type. And if you remember, it was NQ mu N times electric field for N side and PQ mu P times electric field for the P side. So this we have already discussed, and we had a derivation for this too, and this was nothing but sigma, that is J is equals to sigma E. And this is applicable for both type of semiconductor. So if we have, let's say, an N type of semiconductor, this term becomes zero, and if you have a P type semiconductor, the latter term becomes zero. So like that, but we did not. But in reality, if you remember, the J total, that is the total drift, the current density, it has a drift component as well as a diffusion component, right? So we did not discuss the uh, component about the diffusion. So we'll be seeing that in this particular class. So let's try to have some very basic understanding of that. So yeah, so can anyone tell what is exactly is diffusion? I mean, very basic understanding if someone has. What is diffusion? Yeah, exactly. So diffusion is nothing but the movement of particles, let's say from a higher concentration to a lower concentration. For example, let's say in a room, if you apply perfume at the corner of the room, it will move towards the entire room. That is, the particles are not present in the whole room, and it tries to move evenly across the whole room. For example, so let's say this is a semiconductor, for example, and we have some particles, and yeah, these are all the particles there. So due to diffusion, what will happen? They tend to move towards the region which has a smaller or a lesser concentration, and so on. So this particular movement of from higher concentration to lower concentration is what we call as the diffusion. So to derive this, what we do is we use some approximations. So let's say we have a semiconductor, for example, and this is the midpoint of the semiconductor, and this is, let's say, the minus L, and this is, let's say, sorry, let's say L by 2, L by 2, and the length of the semiconductor is L, for example. So if I try to plot the concentration with respect to the length of the semiconductor, let's say this is a midpoint. So let's say I have a particle at the midpoint, which is this. And then similarly, I have a particle which is at the corner. So for simplicity, I'm taking it as L. And let's say I have one more particle which is at plus L. So now what is it is completely based upon the probability that this particle, let's say for example, this particle which is at minus L can go either this side or this side. Similarly, this particle which is at 0 can go either this side or this side. Sorry. And then maybe the particle at plus L can go either this side or this side. So let's say we have a semiconductor and it will not go beyond the semiconductor. So we are not considering it will go outside the semiconductor and not for even this. So if you see, let's say I'm talking about the flow of electron from this particular particle. So this can go this side only, right? So let's say this is the intake for this particular particle. So I'm calling this as F1. So the probability would be nothing but the half times either it will go that side or this side, right? So that is why the half, the concentration at minus L times, so the flow of electrons is nothing but the probability times the speed. Now the speed will be calculated by the time and the distance, right? So L is the distance from here to here, right? And the distance, oh sorry, let's say the time constant is tau c, for example. So this particular thing is nothing but the velocity that we have. So similarly, if I try to have the force, let's say I'm talking this as F2 for this particle, so it will be nothing but again it has half probability that the concentration at plus L will move with the flow of electron would be L by tau c. So the speed will be the same. So this is for x is equals to minus L, and this is for x is equals to plus L. So if I say that the total overall concentration, because one was going, let's say one was going outside, one was going inside of this particle, so the total concentration would be the overall sum or the subtraction of these two, so it will be F1 minus F2. And if I try to write that, it will come out to be 1 by 2, L by tau c is still constant, and it has N minus L minus NL. So this is, let's say, the overall flow of this particular flow of electrons. Now we have already established that this is nothing but your velocity, right? So let's say I'm talking about the extreme case. This is the thermal velocity as of now. So I'm just writing this as VTH. So I can write the overall flow of electrons by VTH by 2, and then again the same thing, N at minus L minus N at L. Now, because this is not a very easy expression to solve, what do we use is we use the Taylor series approximation, which is one of the topic of this course or one of the topic of this particular week content also. So according to Taylor series, what we know is, let's say at x is equals to a very small value a, Taylor series is nothing but, so can anyone tell what is the Taylor series for x equals to a, considering a is very, very small? Anyone have any idea? Okay, so let me write. So it is basically equals to f at a plus x by 1 factorial, f dash of a plus x square by 2 factorial, f double dash of a, and so on. And dash is nothing but dy by dx, for example, the differentiation basically. So this is the Taylor series approximation for the cases when we have a very, very small value. So for this particular case, let's say I'm talking about n at minus L, and I'm trying to calculate the flow of electron at mid. So I will take x equals to 0. So it will be nothing but f at 0. And now the x has become this minus L, right? So this x will be replaced by minus L by 1 f dash of 0, right? So I can write this as f, sorry. So this will be now n of 0 minus L dn over dx. So this is nothing but n at minus L. Similarly, if I try to calculate n at plus L, it will be again n of 0 plus L of dn over dx. So this is just a very basic expansion of the Taylor series. Is there any doubt in this Taylor series expansion? Any doubts? Okay, so if not, now we'll calculate the flow of electron, which is Fn, that is basically equals to Vth by 2 and minus L minus Nl. So I'll do that now. So the total flow of electron is Vth by 2 n at minus L minus n at L. And we have just calculated the value of n at minus L at n at L. Uh, so just replacing these values, so it will be Vth by 2. N at minus L was n0 minus L dn over dx. Then minus n0 minus L dn over dx. So this will get cancelled, sorry. Yeah, so this will get cancelled. Then the 2 will get cancelled also because it is 2 times, and it will come out to be minus L Vth is there and dn over dx. So this is what we have established as a flow of electron. And we know now the current density is nothing but the flow of electrons, right? It is charge times the flow of electrons. And if you remember in the initial classes, we have some formulas that are already established. Mobility is nothing but q tau c by mn star. And then Vth we calculated, if you remember, it was nothing but root 3 kt by mn star, right? You guys remember these formulas, right? Anyone? Am I audible? So I'll just replace this Fn here. So it will be minus LVTH dn over dx. And now what I'll do is I'll use this Q term, which is nothing but, let me see what I can do. So I'll write this as, so VTHL. So now what I'm doing, I'm trying to replace this L by tau c into Vth, that is basically the speed into distance. So it will come out to be minus Q tau c Vth square dn over dx. And yeah, now if I try to write Vth square is nothing but this term, right? So it was not 3 kt, it was kt by m. So Vt square will be kt by m. So now I can write the J diffusion to be q tau c kt by m n star example dn over dx. Now we have just seen that the mobility is nothing but q tau c by m n star, which is this term, right? So I can write the first term, that is a J diffusion, as, let's say, the n-type mobility times kt dn over dx. So now since we know that kt by q is nothing but the Vt, so I'll write multiply and divide by q from here. So using this, what we call, so this mu n kt by q is what we call as the diffusion constant, which is q dn over dx. So this is the J diffusion for the n side, and where this dn is nothing but mu n Vt. So I'm writing Vt Kt by Q as Vt. So this is the n-type component that we have after the derivation for the diffusion side. And similarly, we can also see the p-type component, which will be again exactly the same. It is just it is having the p-type component, so it will come out to be minus q dp over dx. And here dp will come out to be nothing but mu p Vt. So if I can summarize, so for holes, the total current density was J drift plus J diffusion. So it was PQ mu P E plus, and we have just calculated the component which is minus Q dp over dx. And for electrons, Jn is nothing but again J drift component of electron plus J diffusion of electron. So it is nothing but NQ mu Ne plus Q dn over dx. And we know that the total is nothing but Jp plus Jn. So we will have in total four components. So this is how the diffusion components comes out, which is nothing but q dp over dx and q dn over dx. And at the last, what do we see is there is a very important relation that we call as the Einstein relation, which is nothing but, so the dn, as I have just written, it is given by mu n vt, and the dp is given by mu p vt, and we know that this vt is nothing but kt by q. So we say using these two terms, so dn by mu n is nothing but equals to dp by mu p, which is equals to kt by q, which is also equals to vt. This is what we call as Einstein relation. Is there any doubt in this? The whole derivation, is there any doubt? How do we get to these components? So this is kind of the drift diffusion model that is getting solved in your simulator such as TCAD, etc. These differential equations are getting solved. Is there any doubt? Okay. Let's try to have a problem then. The question says, let's say we have a gallium arsenide semiconductor which is doped as N-type, and the doping profile for that semiconductor is given by, it is not constant, it is given by ND naught, which is constant, minus exponential minus x by L. So it changes around, the concentration changes around with respect to, let's say, position, which is from 0 to L. Now the length of the semiconductor is, let's say, 0.1 centimeter. Your ND naught, which is constant, which is this value, it is given, let's say, as 510 raised per 16 per centimeter cube. And let's say the mu n for this semiconductor is 6000 because of the gallium arsenide, centimeter square per volt second. And let's say I'm still talking about room temperature. So the question is, find the induced electric field that generates a drift current density, let's say, which is J drift, which compensates the diffusion current density. So can anyone tell what does this line mean? What do we need to do? This is easy if you try to understand what exactly. Yes. Yeah, exactly. So what do we need to do is we need to compensate the J drift with J diffusion. So we need to either equate them or we need to cancel the effect. So What we need to do is actually your total density, because this is n type, is equals to J drift plus J diffusion. And as she said exactly, so these two needs to compensate each other. So these two needs to be zero. So we kind of need to equate them. So I think you know everything. You have all the values. So try to solve it and let me know the electric field. You just need to apply the formula. It is straightforward. Do you want to try or should I just solve it? Please let me know if you want to solve it. Otherwise, I'll solve. Anyone, do you want to solve it? Okay, so let me solve them. So I have already the n function that is given. So if it is 0, so q will get cancelled out. N is nothing but which is given nd naught exponential of minus x by l mu n e plus dn over dx. Now dn over dx means the differentiation with respect to x of this term, which is nd naught exponential of minus x by l. So what is the differentiation of this term? Can anyone tell? Anyone? Yeah, exactly. So it will be minus nd naught exponential minus x by l, and there will be one more layer because of the exponential nature. Yeah. So this is nothing but this is equals to 0. So now these two terms are common, so I'm just cancelling them. So this has become mu n e is equals to dn by l. Right? And now what do we need to do? We need to calculate the electric field, which is nothing but dn over mu n L. And we have just studied the Einstein relation, which says dn over mu n is nothing but Vt over L. So now Vt is actually given in, I mean, it's room temperature, so it's 0.026, and L is given as zero point 0.1 centimeter. So we'll just keep it in centimeter, zero point 0.1. So the electric field that compensates your drift diffusion is nothing but 0.26 volt per centimeter. Is this clear to everyone? Okay, so let's move ahead. So let's also have some very basic understanding of what is this generation and recombination, because all the other questions will involve the knowledge of this. So as the name suggests, there is some generation happening and then there is some recombination happening. So there is basically generation and recombination of electron hole pairs, which I will denote as EHP in this whole class. So EHP is referring to electron hole pair. So if you have ever worked on TCAT, you might have seen some of the models which are called as SRH, which are called as Auger. So these are all recombination and generation model, Shockley, Reed Hall, Auger recombination, etc. That we apply while solving all of these physics. So what exactly is generation and recombination? Let's see. So let's say I have taken a metal plate, for example, and I have applied energy, let's say h nu energy, which is greater than that of the forbidden band gap of this. So what do you think will happen if I apply energy more than that of h nu? Anyone? Yeah, so there will be emission of electron because we have applied more energy than that of the band gap or the conduction energy. So there will be a ejection of this electron from this metal surface. So what I'm trying to say, let's say in terms of semiconductor, if I apply a energy which is greater than that of the band gap, so let's say this is your valence band, and we know it is full of electrons, for example. Yeah, I'm not making more. And then let's say we have a conduction band. So if I apply an energy which is greater than that of this band gap, so let's say this electron, what will happen? This electron will move from valence band to conduction band. This move electron will come here, right? And once this happens, so what will happen in the valence band? So these electrons were already there, and then there is a occupancy. Sorry, yeah. So there will be a occupancy of. Uh, just a second. Just give me a second. Okay. Am I audible? Okay. Guys, am I audible here? Guys, can you hear me? Okay, okay. Let me share my screen again. Can you see my screen also? Okay, yeah. So what I was trying to say is, yeah, I was telling about the generation recombination. So once you apply energy which is more than, let's say, the band gap energy, so there is this conduction will happen, and this electron will go from the valence band to conduction band, and that will create a hole here, right? So due to this, you see there is a electron hole pair generation that has happened at the valence band. So this is what we call as electron hole pair generation. I mean, these are the very basic terms that I'm trying to make you understand. So this process is what we call as generation of EHPs. And similarly, what will happen? Oh, okay, so if I am applying energy which is greater than that of band gap, and we know this is nothing but hc by lambda. So if I try to have the wavelength, so your wavelength should be less than that of hc by eg. And if I try to put these constant, this comes out to be, so your wavelength comes out to be less than that of 1.24 by eg, which is in electron volt micrometer. So your wavelength should be less than in few micrometers to have this particular phenomena happen. So this is what we call as photoelectric effect also. And yeah, so let's say, I mean, for example, let's do a question for that. So let's say we have a UV light which is having a wavelength of 700 nanometer, for example. And so we need to find minimum EG possible to generate EHPs. So now we have just seen that the condition to have this EHPs is this particular formula, which is we need to have at least this much lambda to have, let's say this is in electron volt and this lambda is in micrometer. So we need to have at least EG, which is electron volt minimum, that is 1.24 times lambda, which is in micrometer, right? So in the question it is given it is 700 nanometers, so this is nothing but zero point 0.7 micrometer. So the minimum EG that we require, so this is has to be less than equals to 1.24 lambda, lambda is 0.7. So it comes out to be approximately 7 7 54 49. Yeah, it will come out to be around 1.72 electron volt. So this is a very basic, that this is a band gap, and let's say we have a, if we have a lambda of 700 nanometers, so this much band gap is required so that there is a electron hole pair generation. Does it make sense to everyone? Yeah. So if I now talk about recombination, because what we know is a material always try to maintain the equilibrium. It doesn't want to get disturbed in any chance. So let's say we have studied, sorry, yeah. So we have studied that at equilibrium we have our mass action law that is applicable, which is nothing but Np is equals to Ni square. So now, but once we dope our semiconductor, so we have just seen that, let's say we inject some of the electron hole pair in a semiconductor, so your N, either N or P will become greater than that of Ni square, right? So now this is actually equilibrium has been disturbed here. So now since we know that the inherent property is to restore equilibrium, so to restore equilibrium, what happens is, so all those generation that are happening are starts to recombine. So this process is what we call as recombination of electron hole pairs. So the definition is the minority carriers recombines with the majority carriers. So here, for example, you will see that this electron that has went up to the conduction band, it will lose energy and it will again recombine with this hole. So the minority carrier, which was the electron there, it combines with the majority carriers, which, sorry, the hole was the minority carrier here. It's get recombined with the majority carriers in the conduction band, that is the electrons. So this process is what we call as recombination. And let me give you a very basic example. So there are two types of recombination that are very important in the course. So one that is we have is very straightforward, which is band-to-band recombination, which is very straightforward as the name suggests, band-to-band. So it happens directly. So I'll talk both about recombination and generation. So as it is written only that, let's say we have some electrons. So these are electrons, for example. So what will happen if I apply energy which is greater than that of Eg, because this is band-to-band. So this will, let's say this will go up, and let's say these two electrons will go up and form here. So this is nothing but band-to-band generation, right? There is a generation of two electron hole pair. So this we also write in short as B2B generation. And now similarly, let's say the electron, because of this inherent nature of being in equilibrium, these electron, what happens is these electron loses energy to come back to their natural state to be in equilibrium. So let's say these electrons come back here so that there will be some recombinations. So this is nothing but, I mean, this is straightforward. This is not much very tough to understand. So this is band-to-band recombination. I mean, the opposite process of generation and recombination that we have already established. So there is one phenomena that we need to study is it is nothing but Auger recombination, because this is the main model that we use in our TCAT device whenever we try to simulate. So it actually happens through impact ionization. So does anyone know what is impact ionization? Any idea? Anyone? Okay, so let me try to tell. So for example, let's consider a case of a MOSFET. So let's say we what do we do is we apply a very high positive drain bias to get more and more current, right? So this is getting more reverse bias, reverse bias. So what does happen? This is results in the increase of the depletion region. And due to this high electric field, there is the electron that are present in this depletion region. They tend to collide with the minority carriers in the p side. So there is a lot of collisions in the electron happening. So let's say this electron is having very high energy, that it collides with another electron. This loses energy and this gains energy. Similarly, this electron will collide with another electron. This will gain energy, this will lose energy, and this happens like a chain. And there is a multiplication of electrons that happens, due to which there is a multiplication of current. So this phenomenon is what we call as avalanche multiplication, or this is what we also call as impact ionization, which is what we call as II in short. So due to this phenomena, what happens is, let's say now since it is not in equilibrium, so let's say this is your EC, this is your EV, and as I said, your electrons are moving with a very high velocity. So let's say this electron. So due to this high energy, what happens? There is first of all the generation, so which I'm not talking about. So once this electron gets generated, they collide with each other and they lose energy, right? As I said, they lose energy. So once they lose energy, what will happen? This electron will come down back towards this hole. So this process that is happening due to the collision and the high velocity is what we call as Auger recombination. The main phenomena due to which it is happening is the impact ionization. So these are the two recombinations that were very important in terms of understanding and what is generation and recombination. So is there any doubt in this recombination and generation? Yeah, okay. So, as I said, that the recombination is happening via impact ionization. Now, you need to understand that impact ionization, what it is doing is, it is causing the collision of electrons. So, these electrons which are there present in the conduction band are moving with very high energy or very high electric field. So, due to which, what happens is they collide with one. So, once there is a collision, you understand that this will lose energy and this will gain energy. It happens like there is a transfer of momentum. So once it will lose energy, this will tend to go back to the valence band because it does not have energy to be at the conduction band. So that is the main thing happening, that once it loses energy, it is coming back to the valence band, and this is how the recombination is happening. This is what I wanted to explain using this diagram. Make sense? Okay. So now, as I said, there are various recombination and generation. So let's try to study some of the topics. So now recombination and generation can happen due to many causes. So let's say this is my uh, semiconductor bar, for example. Okay, let me not make it like this. Make it like this. Let's say there are several recombination generation happening and the flow of electron is like this. So for electrons, so the overall recombination, so it is dependent upon time, obviously. So it can be due to your change in current. It can be due to your, as I said, the concentration change with respect to time can be due to your recombination generation, or it can be due to any other thing that can happen. Maybe let's say a diffusion, drift, any other thing. So let's say I'm writing any other process, for example. Similarly, for holes, the dp by dt, the contribution could be from anything. It can be either from current, it can be due to recombination generation, or it can be due to any other process. So I'm not writing it in. So let's say even if we ignore any other process as of now, we are majorly trying to focus on generation recombination. And due to current, let's say we are at steady state. So okay, so let me try to explain this. So we need to understand that at equilibrium, we know that the semiconductor is stable. So we know that the dN by dt, which is the total case, will always be zero, right? Because we are talking about equilibrium. So at equilibrium, each and every component will be zero. So for due to current will also be zero, due to recombination generation will also be zero. But once we break the equilibrium, there could be multiple components that cannot be zero, but the overall total component will always be zero. That is my point. So let's say we move out of equilibrium. So what will happen? And one more thing I'm trying to emphasize here, that we are in steady state. So can anyone tell what is steady state? Yeah, so no change with respect to time is what we known as steady state. So by steady state, we can clearly see that the dN by dt total would be zero. There could be, since we are out of equilibrium, there could be non-zero component of current or recombination generation. But since we are at steady state, so your overall total change with respect to time will be zero. This is the main point that you need to emphasize. So if it is zero, and let's say since we are at steady state, I'm talking about, so I'll say that the dn by dn total, which is equal to zero, will be nothing but due to, let's say, recombination generation is the only thing that I'm pointing out right now, which is, let's say, generation minus recombination, right? So generation, let's say there are number of electron per centimeter cube per second. Recombination is also some electrons, number of electrons per centimeter cube per second. So as I said, at steady state, this term is actually zero, right? So at steady state, what do we see is that the generation of electron is equals to the recombination of electron, or the generation of holes is equals to the recombination of holes. To just to maintain equilibrium. I mean, this is quite straightforward. Even if we, let's say, apply some excess carriers, or if we inject some excess carriers in any device, your generation and recombination rate will always be the same. Does it make sense to everyone? Okay, so let's try to understand that. Let's say we have a maybe a N type, which is having a let's say a doping of N naught ideally, and the exact excess carrier that we injected is, let's say, delta N. Similarly, for P type, we have P naught actual carriers, and the excess carrier that we have injected is delta P, for example. So first of all, there is two, three phenomena that we need to understand. So the one is for low level injection. Low level, as the word suggests, that we will inject very low level of carriers. So for example, for low level injection, what happens is this delta N or delta P is very, very, very less than N naught. That is, the carriers that we are injecting is very, very less. Similarly, this delta N and delta P will also be very, very less than P naught. So this is an N type because we are now interested more in the minority carriers, and this is in P type. So your recombination time, it is nothing but the number of electrons, excess carriers divided by the time constant. So it will be delta P by tau P. So now, because we are in the minority carrier, so N will be the minority carriers for P type, and your P will be the minority carriers for N type. So as I said, the recombination happens for the minority carriers with the majority carriers. So we are only interested in the minority carriers, right? Does it make sense to everyone? Okay, okay. So let me give you example, maybe that will clear it. So let's say what I'm trying to say is maybe example. So let's say I have a N-type semiconductor, for example, which is having a doping of 10 to the power 15 per centimeter cube, right? So your P naught by default will become 10 to the power 5. I'm talking about equilibrium as of now. So let's say now what I do is I inject some electrons here. Let's say I inject some electron hole pairs which are delta n and delta b are equal. Let's say which is 10 to the power 5, for example. So now your n, the final n, as I have written, it will become n naught plus delta n, which will be still equals to 10 to the power 15 because your delta n is very less. Your P naught, which is P naught plus delta n, it will become twice, right? So whatever is getting changed is actually your minority carriers. There is no effect in general on the majority carriers. So here what I try to explain is that the recombination is happening with respect to minority carriers. Here also I explained here. Let me go back. Yeah. So whenever I said that the recombination, it is nothing but the minority carriers getting recombined with the majority carriers, because the minority carriers are the upper side electrons that are getting combined with your holes, right? So the whole point of saying this is whenever the injection happens, so if I am saying low level, then there is no change in your delta N and P because they will be approximately equal to N naught and P naught. But once you have some high level injection, we are only interested, or the change that will happen actually in the devices will be with respect to the minority carriers. Does it make sense that the minority carriers are getting affected? So I'll give an example also. Let's say, okay, let me actually take an example that will help. So let's say you also try to solve this out. Yeah. So let's say now what I'm saying is again, I'm taking an n-type semiconductor. Let's say my ND is 10 to the power 15. And let's say I'm again taking Ni as 10 to the power 10. So we have studied, let's say we are at equilibrium. So we have studied your EF minus EI, right? What is the EF minus EI? Anyone? It is VTLN, ND over Ni, right? Yeah, so the Fermi level, or the difference between the Fermi level, so this will come out to be 0.026 ln 5, oh sorry, not 5, 10 is for 5, and this I think comes out to be around, let's say, zero point 0.3 electron volt, for example. So now what I'm doing is I'm actually trying to have some high level injection. So let's say I injected 10 receiver 10 12 electron hole pair. So this is the condition. So now what will happen? Your delta n is 10 is for 12 equals to delta p, right? So now my n will become n naught plus delta n, which is 10 to the power 15 plus 10 to the power 12, which is still approximately 10 to the power 15. But my p, which was p naught plus delta p, what was p naught? What will be p naught? Anyone? Yeah, it will be ni square by n, that is 10 to the power 5. But now since I've injected 10 to the power 12 electron hole pairs, so my p has actually become 10 to the power 12, right? So now even if I'm trying to, I did try to calculate this, right? EF minus EI over KT. I got one Fermi level because of this. But even now if I try to calculate P, which is nothing but EI minus EF over KT, right? So I will be having some finite value of EI minus EF. That will be nothing but 0.026 ln, which is 10 to the power 12 by 10. So it is 10 to the power 2. So this is 0.052 into 2.303. So it should come out to be around 0.12 electron volt. So now you see, just because of the injection, we don't have a single Fermi level, and this is what we also called as a concept of quasi Fermi level. If you remember that we have disturbed the equilibrium. So let's say this is your EC, this is your EV, and this is your EI. And initially, what was the case? That it was zero point 0.3 electron volt for EF. And let's say this is was for completely N. But once we inject the carriers, there is one more Fermi level which is zero point 0.12 electron volt below, and this is for P. So these there are two different Fermi levels that we study, and this is what we call as quasi Fermi levels. This we also studied when we moved out towards the positive voltage bias, in which there were two different Fermi levels for two different type of material. So due to this disturbance in equilibrium and the change in the minority carriers concentration, we have the concept of quasi Fermi level. So this is what I want to emphasize, that this is very important. And uh, so yeah, if there is any doubt, please let me know. Otherwise, I'll move forward. Does that answer your question also? That why are we interested in the minority carriers? Okay. Not created, but yeah, yeah. No, no, I did take for N type. So I tried to calculate for both P and N. So if you try to understand here, so this formula was when we have a N type semiconductor, complete N type. There was no injection, right? So there was this Fermi level which was in general, which is present, which is zero point 0.3 electron volt above your EI, which is this case. So I have denoted this as EFN, but since, once I injected this carriers, so let's say I would not have injected these carriers, so your minority carriers, their P naught was 10 is power 5 as you said, right? Due to which, what will happen? If I apply the formula, it was VTLN and A over Ni, which is 10 is power 5 over 10 is power 10, right? So it should have been inside your Fermi, inside your valence band, right? That means there is no Fermi level specifically for P type. But once I inject the carriers, there is one more Fermi level that has arisen, and that is due to the minority carriers. And that is what we call as quasi Fermi level. There are two different Fermi levels because of the concentration or the non-equilibrium. Yeah. So I would say that, let's say your formula was initially EF minus EI, right? So now it will be EFN minus EI over KT. And for P, it would be EI minus EFP over KT. So there would be a dependence after the injection. So this will only happen when we are talking about your low level or high level injection. So now these things, which is related to this question. So your drift diffusion model actually may takes few assumptions. Even we start to solve it. So once it always says that the injection would always be low level, that is your excess carriers will always be less than your N naught and P naught. The second thing that we study is it is always studied at steady state. Third thing is there is always complete ionization of atoms, like there is no atom that has left unionized. And the fourth thing that we study is it is only applicable for non-degenerate semiconductors. So can anyone tell what is this non-degenerate semiconductors? I mean, we have studied, but anyone? You remember we studied about degenerate and non-degenerate maybe in the first class. So all the semiconductors that we are studying till now is not degenerate. What does it mean? That they are moderately doped, right? That their EC, that the Fermi level for N type is below EC, and for P type it is above EF. And for degenerate, what happens is your Fermi level is inside EC. That is, they are very heavily doped. And your Fermi level for P type semiconductors is inside EV. Do you guys remember this? Any doubts here? Okay. So, this problem is actually related to this only. So, which of the following statement is not an assumption made? So we always do it for node unit, so that is actually true. We always consider steady state and we always consider impact ionization, and there is no temperature gradient that is being considered. We always keep it at a constant temperature for the derivation. So your correct answer for this problem is option B. So we'll study this one by one. I mean, there are three, four more derivations which will involve, I mean, that we will study in the next class for sure. So that will involve different cases. Once we'll try to have low level injection, once we'll try to have steady state, once we'll try to have the complete annihilation, and we'll see what is the difference in the actual generation recombination rate with respect to these three cases. So for now, let's say we do know about that these are the three conditions that we will be assuming once we are solving the diffusion model. Because in reality, it is not very easy to solve, right? Because in TCAD, we are solving the differential equation. But in reality, we need to have some solution or the analytical solution to actually make it a compact model, right? In the initial class, I told you that TCAD uses differential equation and some analytical solution to that is what we call as the compact model. So that is why we need to assume some things so that we can have an analytical solution and we can have an actual diffusion model as a part of a compact model also. Is it clear to everyone? Okay. So if it is clear, let's move towards some questions. Let's leave it. Okay, this is a very simple question. So it says which type of semiconductor is preferred for high speed application? Can anyone tell quickly? I hope I'm audible. Can you confirm? Can you confirm if I'm audible? Okay. Yeah. So what do you think is it P type or is it N type or is it both? Oh, it says high speed application. So intrinsic, we do not have any flow of electrons, right? They are ideal. So it could be either P or N. So okay, so I mean this is a very basic knowledge. So it is obviously anti. Why? Because the mobility of N is greater than that of the mobility of P. We know that the effective mass of electron is less than that of effective mass of holes. Hence, for every high speed of applications, we in general prefer N-type semiconductors. Okay, that is not a problem. Hope this is clear. So let's move to a certain numerical. Okay, so this is an easy question. So try this out. It says find the whole diffusion constant, which is dP if you remember. I just did the formula. So Jp is Q dP dP over dx, where your dP was nothing but mu and Vt. For a semiconductor doped with trivalent impurity means it is Na, and its conductivity, so sigma is also given as 1.28. And your Kt is given as 0.026 Kt by Q or Vt. So you need to calculate the whole diffusion constant. This is very easy now. So do you want to try? Can anyone tell how to do this? Yeah, exactly. So mu p will find from the conductivity and then we'll find the diffusion constant. So that is true. So maybe you take 2-3 minutes and let me know if you have any answer and then I'll also solve. Did anyone try? Did anyone calculate mu p? Okay, so since this is p type, so sigma is pq mu p. So mu p will be nothing but sigma by pq. Sigma is 1.28. P is so it's ohm per centimeter. So I'll keep everything in centimeter then. So this your P is 10 per 16. Then your Q is 1.6 10 per minus 19. So this will make it 3. Okay, 16 8 I think is the exact. Yeah, so it's 800 centimeters per volt second. And now your dP is nothing but mu p into Vt. So it's 800 times 0.026, which is 2.6 times 8 is 48, 20.8. And your dP has a unit of centimeter square per second. So it's option A. Is this clear to everyone? Then let's move towards the very simple question again. So just ignore this. So it says a p-type silicon is there, which is having a length of 1 centimeter, width of this, thickness of this, doping concentration of this, mobility of, could you please mute yourself? Yeah. Your mobility of holes is this, and the electric field is this. So it is asking what is the drift current density. This is again very easy, everything is given. Can you even tell how to calculate drift current density for this? I'm talking about drift. Asking drift. So it's nothing but P, Q, mu, P, E, right? Everything is given in the question. So quickly calculate and let me know the answer. Maybe take 1 or 2 minutes. Still no answer. This is very easy actually. Anyone? So P is nothing but Na, which stands for 17. Q is charge, minus 19. Mu P is given 500. E is given 1. So this is minus 2. 1.6 times 5, which is 8 ampere per centimeter square. So option A is the correct answer. Any doubt in this? Let's take one more problem. So let's say what do we have is we have a p-type semiconductor, and it's, let's say it has a concentration Na. So now for the same semiconductor, the concentration of the p-type semiconductor is increased 10 times. So question is, find the change that has happened to the Fermi level, that is EF. So anyone wants to tell what exactly is the question asking and how to do it? First of all, what will happen if I increase the concentration by 10 times? What will happen to the Fermi level? Will it remain same? If I have a p-type semiconductor and if I dope it more, it will move upwards. Yeah, it will move close to the valence band, right? Because we are increasing the doping of the p-type semiconductor. If you would have an n-type semiconductor, then that is true. Yeah, it would have moved upwards or towards the conduction band. So now what do we need to see is we need to find the change. So let's say this was a p-type semiconductor. This is your EC, this is your EV, this is your EI. And your Fermi level was somewhere here, for example. Once you increase the doping, what will happen? It will move closer to the valence band. Let's say this is your new EF. So you need to find the change in the Fermi, that is EF minus EF dash. Is the question clear? Uh, do you guys want to try it or should I solve? Okay, yeah. So now let's say there was a EI minus EF, which was for the actual case. So we know that P is nothing but Ni exponential of EI minus EF over KT. So for this case, your EF minus EI was VT ln Na over Ni, right? Because in this case, your Na was actual Ni. Now what has happened? Okay, sorry, let me use some different page. So here EI minus EF, let me write again. 2 VT ln Na over Ni. Now what happened? Your Fermi level has changed to somewhere else. So your P has now become 10 Na. Because of this, your Fermi level has shifted downwards, and let's say I'm denoting that as EF dash over KT. So now your EI minus EF dash will become VT ln, sorry, this would be 10 Na over Ni. So now to calculate EF minus EF dash, what do I need to do? Let's say this is equation 1, this is equation 2. What should I do? Yeah. So if I do 1 minus 2, for example, so it will give me minus EF plus EF dash, or that is equals to EF dash minus EF. So now we know that EF dash is smaller, so we'll calculate the above, the opposite of that. So we'll do 2 minus 1. So 2 minus 1 will give me EF dash, EF minus EF dash, right? So it will be, what it will be? Can you calculate quickly? So EF minus EF dash would be, if I write VT ln 10 Na over Ni minus VT ln Na over Ni. So what will be this? Sorry? Yeah, so it will be VT ln 10 Na divided by Na. That means it will be 0.026 ln 10, and that is actually 0.026 times 2.303, and yeah, it will come around 0.05 if I'm not wrong. 0.059 you said, I think, right? Is it 0.059? Okay. So your Fermi level has actually went down. So this difference is now 0.059 electron volt. Is this clear? Okay, so let's move. I think let me go towards the syllabus. So we have tried to cover the most important topic, which is the generation and recombination model, but we have not covered the different things, that is, let's say steady state, a complete ionization, and all those things. So since your next week is also dedicated to drift diffusion model, so we'll cover those derivations also in the next week and try to do some problems which are very realistic and related to your assignments in the next week. For today, I think we have covered enough for the understanding. So, if I try to summarize quickly, so we did try to understand how the diffusion terms come from. I mean, we did the derivation, so you should check out this derivation because this is kind of important. And from that derivation, how do we reach towards this J diffusion N and P, and how do we have the whole components? I mean, whole, not HOLE, the WHOLE, all the components for holes and electrons. And then we studied this Einstein relation. Then what do we have? We have this generation and recombination, which is a very important topic because in the next class we'll be discussing the different cases of generation recombination. That is, let me show. Yeah, that is these three cases. We'll be taking assumptions and solving them one by one and seeing that how does our recombination behaves once we have these three different cases. And yeah, and then we covered then some of the very basic semiconductor problems that are there already in your this syllabus. So yeah, so this was EF dash minus EF 0.059. So this difference was 0.059. So if you don't have any doubt, I think we can wrap up the lecture session for today. We'll meet then same time in next week. Is there any doubt? Let me stop the recording.